Welcome back, everybody. We're going to pick up with Bayes' risk example. This example is in your book, and it's alluded to on midterm 2 as well. So this will help you a little bit with it. But this problem is in the book. And then we're going to jump over to the Cramer route lower bound. I'll motivate through an example that's also in the book, and then we're going to derive the Cramer route lower bound, which is a lower bound on variance. So imagine you like MSE, L2. Basically, you're saying that, well, let's say this. Let's say you have an unbiased estimator. So let's assume you like unbiased estimators. A lot of you have told me you like unbiased estimators. And let's say you also like the L2 loss function, so mean squared error. If you like those two things, basically you're saying you want to minimize the variance on something. So one way you could go about it is you could go collect every estimator in the world for some problem, and then you could find the one that has the lowest variance. And that would be nice if you could do that. So, but there's a lot of estimators out there in the world, so you'd be doing this for an infinite amount of time. So it'd be nice to know if you found some estimator with some particular variance. It might be nice to know that you could never go lower than that variance. And Cramer route is sometimes applicable to these cases. So we'll discuss that a little bit. But let's pick up with this beta Bernoulli example. I usually call it the beta binomial sort of thing. Bernoulli, the binomial, same difference to me. So I get a whole bunch of observations. I want to estimate what P is. Okay. Before we do a Bayesian analysis here and discuss Bayes' risk, the MLE, so I'll just say P hat MLE is equal to X bar. That's just sum of the Xi's over N, and you can check that out. And so if we like L2, so I'm going to assume we like L2. I'll say squared error loss just to say it a different way. So assume we're using squared error loss, then the risk for our estimator is going to be the bias squared plus the variance. This estimator right here is unbiased. The bias for this estimator is 0. So the risk is just the variance. The variance for our example for X bar N is equal to P times 1 minus P divided by N. The bigger N is, this thing gets smaller. We can all derive that. Now we might want to know, could we go lower than this? And where might we go lower? So this right here, does anybody know what this looks like? Sure, you can plot it. This goes between 0 and 1. It's right here. This function maybe looks like this. So that's my risk function. This is over a function of P. So if I plotted this thing, this is an upside down parabola. You could probably convince yourself of that. There's a quadratic term in here. So P squared, which way is it going? It's flipped upside down. There's a negative sign. And it looks something like that. And so what it's saying is that my risk in my estimator is high over here and low over here. And maybe that's nice. So this is kind of an interesting thing to think about. So P was 0 right here, and I used my estimator, X bar. X bar is going to be 0 because all the x's will be 0. P was equal to 0. And I have little risk, i.e. identically 0 risk in using that estimator. It's kind of a funny thing because usually we start thinking about the endpoints giving us problems. And they do. If I were to construct intervals using this estimator, I'd go horribly wrong. And that would be poor. So the variability does help us in estimating things, distinguishing things for us, but the risk over the middle is higher because the estimator is going to be more variable. It's going to jump around a little bit more. So think about that a little bit. The question is can we go lower and where would we go lower? So maybe we like risk functions that maybe look like this. Constant risk across the whole space. And that would be some sort of a compromise. So might want to know how do we build an estimator with lower risk. So I might be able to bring down the risk over in this region, but I'm going to pay a price for it over here. And so we want some flexibility in developing our estimators. What I'm going to show you is Bayes can give us that flexibility. It's not the only thing in him, but there's a couple knobs in a Bayesian analysis. And our knobs are going to come through the prior and the hyperparameter. So we can turn those hyperparameters and get different risk functions depending on what we want to do. So I'm not going to say that a constant risk estimator is your best estimator, but there's some desirability there. Maybe I want it to perform equally across the whole space. Okay. So in a Bayesian analysis, we're going to form the prior. So for Bayes, we're going to choose a prior, we're going to build the likelihood, we're going to multiply them together and recognize that distribution. So the posterior distribution in our case, under that prior, I'll say P given X, this is going to be a beta distribution. And it's going to have some parameters attached to it. So this is going to be sum of the xi's plus alpha. And this is going to be n minus sum of the xi's. I goes from 1 to n plus beta. And we've worked that out many times now. We can develop some estimator out of it. So if we're using squared error loss, the L2 function, then the optimal estimator is going to be the posterior mean. Now I need to go back and show you a little bit about this, that that's actually true, but I've stated it. Next time we'll come in and maybe prove this statement. So under L2, the posterior mean is optimal. So i.e. what I mean by that is if I look at the Bayes risk, let's just write it out like this. I'll write down my risk function for my estimator, given P. This is going to be my estimator. It's a function. This is my parameter. And then I'm going to multiply it by my prior. And I'm going to integrate over the prior. I'm going to go between 0 and 1. So this is my Bayes risk right here. It's going to be this thing. What I'm going to try to do is I'm going to try to optimize this. So E, my estimator, I'll just say in our case, let's call it a key half Bayes, is going to be the arg minimizer over my estimator right here of this thing. R, E, key, pi P. So what a Bayes estimator does is it minimizes the average risk. I'm just going to write this down. This is average risk. Which average? The average that I get from averaging over this prior. So my prior is placing weights on the space. How much weight is it placing on the space? It looks something like, well, it depends on which alpha and beta I pick. But there's a lot of flexibility in here on how I pick that. So I could equally weight the space by picking alpha and beta to be equal to 1. That's going to be a uniform distribution over the whole space. Maybe we use my favorite prior, beta half-half, and that's that U shape. So lots of flexibility. So Bayesians, what they're doing is they're just optimizing the average of something. Sometimes people talk about Bayes optimality. What they're saying is that Bayesians are optimal on average. So Bayesians are averagers. They're always averaging over things. Just point out what risk is again. Risk is just the integral of my loss function with respect to my sampling distribution, where I integrate out x. So I'm looking at the average performance over lots of different data sets. So I haven't proven that the posterior mean is the optimal answer right here, but what you have to do is just optimize this thing. I'll do it next time and I'll show you how to find those optimal estimators. But let's just go with the fact that the posterior mean does optimize this. It's probably not that surprising to you. So our posterior mean, in this case, is just going to be sum of the xi's, I goes from 1 to n, plus alpha, divided by alpha plus beta plus n. And you work that out. And so our Bayesian estimator looks a lot like this, but it's been regularized, i.e. the hyperparameters are adding something to the function. As n goes to infinity, that answer looks like this answer. So there is some agreement. Saying that, when n is a finite number, they're different. Close but different. So what we need to do for our Bayesian answer is assess what the risk is. So we need to look at the risk for p hat phase. So I will point out that a lot of Bayesians weren't converted to being Bayesians through the whole principle of likelihood times prior and saying things like it's intuitive to think about it like this. That may or may not be true. But a lot of people have become Bayesians because of the decision theory characteristics. So if you want to optimize something on average, then you're going to be a Bayesian. So and I'll show you some of these cool features about doing that. So we need to look at this risk function. That's just going to be the bias for p hat squared, or for p hat phase. This is going to be the bias squared plus the variance for p hat phase. There's a little bit of work to do. This isn't too hard to work through. So this is going to be the expected value of p hat phase minus p squared plus the variance of p hat phase. So let's do it. Let's figure out what that risk function looks like. So I'm just going to rewrite this. I'm going to let this and give us some notation. I'm going to let this equal to y. Just to shorthand my notation. Let's just plug everything in. This is either a really hard problem or a really easy problem, depending on if you know about sums of Bernoulli. plus alpha plus beta minus p squared plus the variance of y plus alpha over n plus alpha plus beta. That's what we're looking for. Again, all of this is in your book. So the expectation is only operating on the y's, and the variance is only operating on the y's as well. That's the random thing in all of this. So expectation of y, what is it?
NP.
NP. Easy stuff. So we'll use that. So this is going to be NP plus alpha over N plus alpha plus beta minus P. This whole thing is equal, and then I have this plus right here. This is squared. There's some quadratic function over P. The variance of y, I think we know what this is as well. What's that?
NP times 1 minus P.
NP times 1 minus P. And so I need to square this stuff out when I do everything. So I'm going to have 1 over n plus alpha plus beta squared. When I take the variance and I add alpha to it, it doesn't change anything. So this is going to be n times p 1 minus p. And that's what my risk function looks like. And now I can play around with this. So I can start plotting it and think about what this thing is. What we could also do is if we wanted to find a constant risk, what we would do is we take this function right here, and I'm just going to write down that this is going to be my risk. It's a function of p. It's going to be equal to this whole thing. So what I would do is I would take a derivative with respect to p of my risk function, and I'd set it equal to 0. And I would solve for alpha and beta. So oftentimes a Bayesian is doing something like this, where it's what are the hyperparameters? That's always been a question that we've been thinking about. How do I pick the hyperparameters? What am I doing with them? It depends on the properties you want out of your analysis. So this would derive a prior such that the risk looked constant right here. So this risk function, when I solve for everything, will give us this. And I can say a few things about this. I can say that if anybody has any other estimator out there, I'm going to beat you somewhere by using this estimator. Let me just say that again. Using p-hat Bayes will beat any other estimator somewhere. So we're not saying we can beat every estimator everywhere, but we're we're saying any other estimator you show me, I've got you beat somewhere. That's kind of a desirable property. We would not want an estimator that gets beat everywhere. If you do that, if you're going to be beat everywhere, use a different estimator. If there are estimators you probably use that I can beat you everywhere, we can have that conversation offline. Probably just don't know it yet. So why can I say this? Why is that true? This actually has a technical definition attached to it, i.e., p-hat Bayes is admissible. So if you can beat every estimator somewhere, you're said to be admissible. If you're beaten everywhere by some other estimator, that estimator is said to be inadmissible. So Bayes estimators are admissible, always. There's a little caveat to it. The prior I have to pick has to be, it has to integrate to one. You might think that's true of all priors. It's not. Don't worry about that. We'll talk about it in Bayes class. So if your prior actually integrates to one, i.e. it's proper, that's all the priors we've discussed in this class, then your estimator is admissible. Why is that true? Think about the definition of what a Bayes estimator is. I optimize the average risk. So if it's best on average, it has to be best it has to beat something somewhere. So I'll just write that down. Since it's best on average. So if I have an estimator that on average is lower than everything else, then it must be lower somewhere as it's compared to something. If it's going to be lower on average, it has to be lower somewhere. Does that kind of make sense? That's the property of averages. So I could come up with a technical proof of this statement, but I think we can state this fairly intuitively and believe it. So lots of flexibility in choosing these alpha and betas. So you might think about just plotting the risk function as a function of all of this. If I wanted constant risk, then I can just do this calculus problem. Here's kind of another fact that you might not know about. Minimax. Sometimes instead of minimizing the average risk, some people want to minimize the maximal risk. It turns out the estimator pertaining to this constant risk is Minimax. It minimizes the maximum risk. We won't prove that. The MLE, however, is not Minimax. It does not minimize the maximal risk. So the Bayes estimator pertaining to the constant risk function is best on average, and it also minimizes the maximal risk. Turns out the maximal risk is always this height right here. So you're always obtaining that maximal risk. So some people call this the least favorable Minimax estimator, but it's still Minimax. So I'll just write that down as just a note. Note. P-hat Bayes for alpha and beta such that the risk is constant is, I'll say, minimizes the maximal risk. I'll give you the name for this, Minimax. Maybe you've heard that statement in colloquium. I've got a Minimax Estimator or something like that. Turns out, for any Bayesian analysis, I can use this mechanism to derive a Minimax Estimator. If I make the risk constant, it will be Minimax. For this problem, I would encourage you to work this out. This is going to be, when you solve for all of this, this is square root of n over 2 is equal to alpha is equal to beta. So I kind of like Bayes because it gives me these knobs to play around with. And I can kind of change what my analysis is doing depending on how I set those hyperparameters. I also get joint inferences on my parameter sets, and I also follow the sufficiency principle. It's all baked in. I like that. It also keeps me in bounds so that I'm not driving estimators that have really poor performances, that live in some range where the parameter can't live. Mom estimators sometimes violate that. These estimators never do. So there's a lot I get for free when I do a Bayesian analysis. Anyway, if you want to be best on average, do Bayes, but think about how you're averaging things, because it matters. Saying that, if you use a proper prior, i.e. this does the things probability distributions are supposed to do, then you'll beat everybody somewhere. You might not be at the same place. Okay, I think there's enough about that. Lots to think about. We can fill a whole class on decision theory, come up with lots of theorems, so on and so forth. What I want to say is, what we really want to do sometimes is control variability. And we want to know how low we can make the variability when we start deriving estimators. And the Cramer-Rao lower bound says something about that. So let me just state what the Cramer-Rao lower bound is. So, let me go back. Say I have some data. X, i's are going to come from some model. So I'll say x1, and write it like this. X is going to be x1 to xn. And these are going to be coming from some model, fx, given theta. And then I'm going to give you a few conditions. So let me make sure I use the same notation as in the book. Wx be an estimator that satisfies, and this is really important, Cramer-Rao does not hold if this condition is not satisfied. So the derivative with respect to theta, expectation of w, x, I'll just be clear, my expectation is over x given theta, is going to be equal to the integral Wx d theta fx given theta dx. So we need this to be true. So if you have an estimator that does not satisfy this condition, do not apply Cramer-Rao. It doesn't mean anything. I oftentimes will give you problems, and I'll set you up to, this would be a typical sort of final exam thing that I might do to you, is I might set you up in a problem, I say derive the variance, derive, the bias of this estimator, and then I'll say something like, what does Cramer-Rao say about this? And give will work through and they'll work out the Cramer-Rao lower bound, they'll do the calculation, spend a lot of time, and then conclude something with the Cramer-Rao lower bound. And it turns out this assumption isn't satisfied. And the answer to the question is, it says absolutely nothing. So no math to be done. So always check this condition. This is the Cramer-Rao lower bound. We'll talk about this condition in a second. The Cramer-Rao is going to put a bound on the variance of Wx. So we're thinking of Wx as some estimator that I'm going to come up with. The bound is this. Something squared here. It's going to be the derivative of d theta expectation of Wx. Let me be clear, this is that right here. So this whole thing is being squared. Divided by the expectation of the derivative of the logarithm of fx given theta. And this is going to be squared in here. This is kind of a nice result. So I'll say something about this in a second. But this is always true, so long as this is true. So this gives us a theoretical lower bound on the variance. The nice thing about this bound is it's oftentimes attainable. So in mathematics, we derive bounds all the time, and those bounds can't be obtained. So let me give you an example. This is Scotland's theoretical lower bound on variance. If you use this result, please cite me appropriately. So, Scotland's lower bound. This is also true. Variance of Wx is going to be greater or equal to 0. That's a theoretical lower bound on variance. Can you prove it? Okay, I proved it a long time ago. I'll see if I can dig it up for you guys. This is obvious. Variances are always possible. So this is not useful to say this. Well, I know that the variance could, if it's bounded by 0, not useful. This bound, however, is oftentimes attained. So if I derive an estimator that meets this lower bound, what it means is I can never find something smaller than it. So I will say this without working through the calculation. We'll probably do this next time when we come in, is this example. Just a quick example. Xi's come from a normal model, mu, variance, sigma. And I'm going to say that's known. So maybe I do a lot of work. I see n data points. I do the MLE, or I do some Bayesian analysis, or I do some sort of MOM estimation, and I convince myself that an estimator, Wx, is equal to x bar, n, just sum of the xi's, over n is a good estimator. So I've got some method for deriving this, and then I figure out the risk. Well, I should say the variance. We already know that this is an unbiased estimator, but the variance of Wx is equal to sigma squared over n. That's the risk. It's unbiased. So the variance is the risk under an L2 assumption. It turns out this thing right here if I went through all the math for my model, I would find out that this thing is equal to sigma squared over n. If I worked out this left-hand side. What that would tell me is that I can't find an unbiased estimator that has smaller variance, no matter how hard I try. So this would be useful. So what it would say is if I like L2, and I like unbiased estimators, I can't beat that. That's optimal. And we would show that by working out this left-hand side. And so we could just stop. There is some math involved in whether or not an estimator can obtain the Cramer out lower bound. We're not going to test on that in this class, but there is a section in the book, and I would encourage you to read through it, what the attainability condition is. It's basically going to unpack the proof that I'm going to show you in a second.
Is Cramer route specific to the L2 loss?
It's specific to variances.
Okay.
So it's specific to variances. So it's specific to an estimator with a certain bias level.
Okay.
And so for a certain bias level in an estimator, it's a bound on the variance. Now, if you think the bias level and variance are the only important things, then you're thinking L2 loss. So, kind of. It's really specific to the variance. I want to just point out that if we had an unbiased estimator, this thing would be equal to theta if it were unbiased. When I take the derivative with respect to theta, that's 1. And so for unbiased estimators, the numerator is 1. I'll just write that down. It's equal to 1 for unbiased estimators. So the bias level is coming in the numerator. So this expectation is going to tell us what the bias is. Does anybody recognize the denominator?
It's the log likelihood squared.
Say it again?
It's the expected value of the log likelihood squared.
That's true. Almost.
It's like something to do with information, right?
Yeah, it's Fisher's information. This is called the expected Fisher input. Most people just call that Fisher's input. So that's kind of cool. So what this says, if I'm working with an unbiased estimator and the numerator of this thing is 1, the Fisher information inverted is a bound on the variance. A lot of people use that result very directly, that they'll be estimating variance, and they'll just plug in the inverse of Fisher's input. So this can be used as an inferential technique. And asymptotically, that might be good. Saying that, I don't do that. But if I were a statistician in the 60s, I might do that. I'll say more about that later. What we need to do is prove this statement. So let's just do it. It's just a few lines of math. Proof of Cramer route. Then we'll look at some examples. But I think let's just start with a proof and just show that this thing is true. I will say this is really just an application of Cauchy-Schwarz. I'm sure in calculus class you saw Cauchy-Schwarz inequality, and it has to do with inner products. This is exactly the same thing, but it's in a statistical context. It says this. This is that same inequality you've seen before. It's just being used in a slightly different context. It says the covariance between two random variables squared is going to be less than or equal to the variance of x times the variance of y. Is that obviously true to you guys, or do you want to see it proof? Everybody wants to see the proof. So let's do it. So just look at this. So the covariance of x and y divided by the square root of variance of x times the variance, square root of the variance of y is going to be equal to, I'm just going to call it something rho. Does anybody recognize what this statistic is?
Correlation.
This is correlation. So my proof is going to require you to know something about correlation. Where does correlation live?
It's absolute values between 0 and 1.
Yeah, that's right. So this thing is going to be bounded between -1 and +1. Right here. If I square everything, we get back to this. So I'm going to conclude my proof with that statement. So if you know what correlation is, this is automatic. If you don't know what correlation is, prove to yourself that this thing lives between -1 and 1. So I'm just going to conclude that. We'll use that in a moment. So we'll come back and we'll use this statement right here. But that's Cauchy-Schwarz for statisticians. It's basically a statement about correlations. Okay. I'm going to prove something else very generally, and then we're going to recycle this thing like 3 or 4 times throughout my proof of Cauchy-Schwarz. The book does something slightly different, and I'm going to try to unconfuse what the book does. This is just in general. It's a general statement. So in general. But we're going to assume this as well. So this thing that I call star now, like in general. So long as star is true. So I'm going to say the derivative of the expectation of some function g. The book calls this w when they show this step, and then they interchange w a couple times. So I'm going to just call this something different, g, and then I'll substitute for g later on. So this is going to be the integral of gx, derivative of fx given theta. Let me just ask you, this assumption that we're making, does it feel natural to you, or are you just like, where does this come from? This is saying this. So this thing right here is just the integral of gx fx given theta dx. That's what that expectation is. So when I take the derivative of this thing, I write it down like this. This statement is saying that I can flip the order of these two things. I slide this through the integrand, over the integral, into the integrand. There's no thetas here. That wouldn't be a very good estimator if it involved theta. So you presuppose you knew what theta was, and if you did that, then that's not estimation. So then I just slide the derivative over here, and it's right here. Does anybody know what this result is called?
Leibniz?
What's that?
Is it Leibniz?
Maybe. So I don't know. I don't think so. I've never heard it called that way. This is Fubini's theorem. And this is true under a certain number of conditions, like everything in here is positive, or its integral is finite. This will always be true, so long as theta doesn't live on the bounds of the space. So in a problem where theta defines the bounds of the space, this won't be true. But in a lot of cases, this is true. This is Fubini's. It's not always true. In examples where theta lives on the bounds, like a uniform between 0 and theta, we can't apply Cramer. theorem holds, then the Cramer-Rao lower bound will hold. I'm just going to rewrite this a little bit. So let me just do a step. I'm going to divide by f of x given theta, and I'm going to multiply by f of x given theta. So I just multiplied by a funny form of 1. Yes. So I haven't changed anything. And I'm going to reinterpret this real quickly. This is going to be the expectation of gx derivative with respect to theta f of x given theta divided by f of x given theta. So I'm just taking this stuff right here, I'm integrating it with respect to this. So this is the expectation of that stuff. That's all the same. So I've written down the expectation a little bit differently, but they're identical to each other. I'm going to rewrite this again. This is going to be the expectation of gx times the derivative of the logarithm of f of x. Keep Cauchy-Schwarz up. Take away this proof. Exactly the same thing, I've just rewritten it. So derivative of the logarithm, which logarithm? It's the natural log. So the derivative of the natural log is 1 over that thing. Then I have to do chain rule. So they're the same. Okay. Here's where the book gets a little bit funny. Book is going to take g is equal to 1. But this is a true statement right here. So this thing right here is equal to that. So let g of x for a moment be equal to 1. Then what we just proved is that the expectation d theta of 1 is going to be equal to expectation of the derivative of the logarithm of f of x given theta. So I'm just substituting in g right there. Somebody help me out with this. What is this thing? It's 0. So expectation of a constant is the constant. Derivative of a constant is 0. So I've just proven that this thing is equal to 0. We're going to recycle that several times. So now I'm going to look at something. We'll almost have this proved. So we're about 2 steps away. So I'm going to look at the covariance of wx and the derivative of the logarithm of f of x given theta. This right here is just the expectation of wx times the derivative of the logarithm of f of x given theta minus the expectation of wx times the expectation of the derivative of the logarithm of f of x. That's just a definition of what covariance is. You should be familiar with that. So I've already proven that this is 0. So this covariance right here is equal to that. I think we should probably finish this up next time. But if you want to stick around, I can finish it now. I'll come back and I'll pick up with this step, but since I'm right in the middle of it, I'm going to finish it and it'll just take me about 2 or 3 minutes. So I'm going to just think about this, Cauchy-Schwarz. So Cauchy-Schwarz says that the covariance of Wx and the derivative of the log f of x given theta divided by, and I'll just square this thing out, squared divided by the variance of Wx times the variance of the derivative of the log, I say likelihood here simply because I'm operating on theta. As soon as I operate on theta, I think this is a likelihood function. It looks like you're sampling density, but I'm operating on theta, so I'm thinking about it slightly differently. So this thing is going to be bounded by 1. That's what Cauchy-Schwarz says. So I'm just going to rewrite this. This is the variance of Wx. That's our statistic. This thing right here, we've already shown what the numerator is. This has a different name. It looks like the expectation of Wx times the derivative of the log likelihood. Squared divided by, and I'm going to rewrite this real quickly. I'll do it right over here. The variance of the denominator, so determine the denominator. I'm going to rewrite this for you. This is going to be the expected value of dd theta log fx theta squared minus expected value. That expected value is going to be squared. Derivative dd theta log likelihood. I've already said what this is. This is 0. So this variance is that thing. I'm going to write that down. Expectation of the derivative log fx theta squared. This is Fisher's info. This thing right here, we have another name for it. And we've made a proof about this already. So we're recycling the same thing, the first step I did in my proof. That this thing right here is equal to, I'll just write down, the numerator is the derivative d theta expectation of Wx squared. So this expectation expectation, in our first step, we said is that expectation. Divided by Fisher's info. Log, likelihood, derivative, and this whole thing is squared. But this is squared inside. And we just showed that it's less than that. I probably should do that slowly, but I think it's useful to see it a first time. Next time I'll come in with this on the board. We'll write it out again. We'll look at those steps again, but essentially we just proved that. So apologies for going over. I'll simplify that a little bit for next time. Study the proof. It's in your book. So you can read through it. They do it slightly differently than I just did it. We'll come back next time. We'll talk about Bayes' risk. We'll talk about this proof one more time, recap what we've just said. Then I'm going to move on to what's called the Raoult-Blackwell-ization. So the Raoult-Blackwell theorem. And I'll tell you how to use that theorem as well. So we'll look at a couple examples here next time as well. That should help you with the midterm a little bit. Thanks, you guys, and have a great weekend.